Hey guys, welcome back. For this video, we're going to talk about shapes of graphs, and this is actually the first part of two parts for lesson 3.5. Look at the goals for the day. We're going to determine whether functions have line symmetry, and if so, find the line of that line of symmetry. We're also going to try to identify the extrema and where the functions are increasing and decreasing. Then we're going to look at the vocabulary. We got line symmetry, increasing, decreasing, extrema, relative min or max, and we'll talk about those when we get to the graphs. Take a look right here. We've got some vocabulary. A figure has line symmetry if each half of the figure matches the other side exactly, and what we really mean is if we draw a vertical line, can the graph fold over on itself, and if it does, then it's got line symmetry. And we've got increasing. That's where a graph of a function goes up when viewed from left to right. Now, you see they don't have decreasing there. That's because that's where the graph goes down when viewed left from right. We've got extrema, and that's the points that are the locations of relatively high or low function values. Then we've got end behavior. That's the behavior of a graph at the positive and negative extremes of its domain. Okay, so for a big portion of this video, I'm going to use the Desmos calculator here to explain lines of symmetry. First thing we need to know is that lines of symmetry are defined by vertical lines. And if we have an equation where we have y equals x, you'll see that that creates a diagonal line on the graph. If we put y equals some constant value, like 5, you can see that creates a horizontal line. Well, lines of symmetry are vertical lines, so we got to change that to some kind of x equals a constant value. And you can see that we have a vertical line there. To demonstrate this, though, I've created this vertical line that allows me to move the line left and right quick and easy here. So our first graph, we have this diagonal line. This is a linear equation or linear function. And as I move this across, you'll see there's no matching parts on the left and right hand side of that vertical line. And here's what we really mean. If you go from the vertical line to the left and you hit the graph, then there should be a matching part on the opposite side that's reflected across that vertical line. And you'll see there's no matching parts that go across there. So the linear equation or the linear function has no line or axis of symmetry. For this next graph we have, or this next function, we have a second degree, which creates a parabola. And you can see as I move across there appears to be some sort of symmetry. As I move across, let's say right about there, the distance from that line to the graph on the left matches the distance from that line to the graph on the right. And if I go down to the axis, the same thing happens down here. I got the same distance on both sides, so it looks like we have vertical line symmetry. To know what that line is, we want to look down here where it crosses the x-axis, and it crosses at -0.5. So when they ask you to define the line of symmetry, the axis of symmetry for this function, this parabola, is where x equals -0.5. This is our axis of symmetry, or our line of symmetry. For our next function, we have a fourth degree, means x has been raised to the fourth power. As I move the line across and I come to this first change of direction, it doesn't appear to be symmetrical on the left and right hand side, nor does it appear to be on this side as well. However, right here in the middle where it changes, we appear to have some sort of symmetrical property. So if I look across here and I look across here, it appears to be the same distance on both sides. Same thing here and here. Even the inside portion right here is symmetrical, or mirror images. And even if I went all the way to the other side through there, I still have symmetrical properties. So what is the axis of symmetry, or the line of symmetry, that this graph has? Well, we look down at the x-axis right here, and we can see it's +1. So the axis of symmetry would be where x equals 1. Remember, we're defining our axis of symmetries with a vertical line, therefore we must define them with x equals some constant value. Here we have another fourth degree function, or fourth degree polynomial, and as we move across, there does not appear to be a vertical line that reflects the left and right hand side of the graph, or in other words, the graph can't fold over on itself. So this one has no line symmetry. And for our last one, we have a third degree or a cubic function. And this one appears to have no lines of symmetry either. Even if I try to cut this right down the middle, let's say right about there, when I look on the left hand side of my line here, that image right here should be reflected equally over here, and you'll see there's nothing over on this side of the graph. Therefore, this one has no line symmetry either. All right, now on example 1, determine whether each function has line symmetry and explain. Well, we can see that the first one here is a linear equation, and no matter where I draw vertical lines, there's no line of reflection. So there is no line that can be drawn to make the right half of a mirror image to the left half, so the function does not display any line symmetry. The one over here on the right, though, it looks like if I draw a line right here, the left and right hand side are mirror images of each other. So the function is symmetric in the line of x equals. If you look at that a little bit closer, that's 1.5 there. So x equals 1.5. The other two, we have a parabola again. It says the function is symmetric in the line of x equals. Draw a line right here. And that looks to be 1, 2, -2. So x equals -2. And the one on the right, that is another cubic. There is no line that can be drawn to make the right half of the function a mirror image of the left half. So the function does not display any line symmetry. Go ahead and pause the video and attempt to check. This one's on page 180. Okay, for this check, we're going to examine the function. Part A, does the function possess line symmetry? It does appear to possess line symmetry. If we draw a line right down the center here, you can see that this side right here is 3 units to the left of center, and this one is 3 units to the right of center. And then we can do it again on the very top here. We've got 5 units to the left and 5 units to the right. So this one has line symmetry, so the answer there would be yes. Describe the line symmetry, if any, of the function. Okay, so remember that the definition of our axis of symmetry is a vertical line. So we're going to start off with x equals. Then we look back at the graph. Where does that vertical line cross the x-axis? Well, it crosses at 3. So our line of symmetry is at x equals 3. Okay, for example 2, they want us to interpret the symmetry. So a fountain is spraying a stream of water into the air. The solid portion of the graph represents the path of water. Now remember, the water comes out of a fountain. It goes up, and then it comes down and it hits the ground. That's why this part of the graph down here is ignored, because negative values of y don't make sense. And this side of the graph is ignored because negative values of x don't make sense. Now they're telling us that x is the distance in feet from the fountain. So x is the distance this way in feet. And y is the distance in feet vertically that the fountain is above the ground. So y is going this way in feet above the ground. So they want us to find and interpret any symmetry in the graph of the function. The right half of the graph is a mirror image of the left half in the line x equals. So we're looking down here. And it looks like it has line symmetry right here. And that goes to the 2. So x equals 2, and that's 2 feet. In the context of the situation, the symmetry of the graph tells you the height of the stream of the water when it is 0 to 2 feet away from the fountain is the same as the height of the stream of the water when it is 2 to 4 feet away from the fountain. So what that means is if we look at the 1 foot mark here and we go up, we see that the water is 8 feet across, or 8 feet above the ground. But if we also go to 3 feet and look across, we see that the water is also 8 feet above the ground. So it's symmetrical on both sides, same height. Go ahead and pause the video and attempt to check. Okay, so for golfing, the solid portion of the graph represents the path of a golf ball after it's hit off a platform, where x is the distance in feet a golf ball travels, and y is the height in feet of the golf ball. Part A, use the graph to describe any symmetry of the graph of the function. Well, it looks like it has symmetry right about here. And we can clearly see that that's under 100. So out of our answer choices, the one that's closest to 100 but not going over appears to be choice D. For part B, they want us to interpret the symmetry in the context of the situation. So if we go back to our graph, we can see as the ball is traveling upwards, it's going a certain height above the ground, and then it reaches 90 feet across the ground. Remember, it's 90 feet this way across the ground. Then the heights on the left-hand side are the same heights as the right-hand side till it gets another 90 feet. So another 90 feet over here would be at 180 feet. So these heights are all the same as the one on the left because it is symmetrical. So our answer choices, and it looks like we've got two that are pretty close. We got B and we got D. The difference is the first one talks about the height of the ball when it's traveled is the same height as the ball when it goes from 90 to 180. The other one talks about the distance it has traveled. Well, the distance is a different question. We are talking about the heights. So the choice here has to be choice B. Okay, so this next part here talks about the extreme of the graphs, but we're going to actually talk about that on the second part of the video, or the part 2. What we're going to focus on right now is increasing and decreasing. So I'm going to go back to the Desmos calculator, and we're going to show what that means on the calculator. So here we have the second degree polynomial, which creates our parabola. It's called a quadratic. This is the one that was in the earlier part of the video. As I move the line in from the side, the vertical line, you'll see it starts tracing the intersection. And what I want you to notice about this as I move from left to right, the x-coordinate is going to get bigger as I move from left to right. But also the y-coordinate is going to get bigger as well as I move from left to right. So watch that as I slowly move it across the screen. Notice that the y-coordinate is getting bigger, so is the x. And it's going to keep getting bigger and bigger and bigger and bigger, right up until we hit that line of symmetry. And that line of symmetry was at -5, or -0.5. So if I were to continue moving from left to right any further, this y value will actually start to go down. So where is this graph increasing? It's at this point right here that the y values kind of reached a maximum value. If I go any further to the right, the y values will start to go down. So where is this graph increasing? Remember, it was increasing as I went from left to right along this curve, and it stopped right here, and it stopped when the domain was -0.5. So where's this graph increasing? Well, it's increasing everywhere the domain is less than where that axis of symmetry happened to be, which is at -0.5. And I say all my x's are less than, that's where it's increasing. So where's this graph going to decrease? Well, as I continue from left to right, my y values get smaller and smaller and smaller again, but my x values are still getting bigger and bigger. So where's this function decreasing? Remember, my axis symmetry was right here, and that was at x equals -0.5. So this graph is decreasing everywhere to the right of that location on the x-axis. You can see here my y value went back to a negative as I got down there. So where the graph is decreasing is when x is greater than -0.5. For example 3, they want us to determine where the function is increasing and decreasing. So when we look at our graph over here, we want to find the axis of symmetry first, or a change of direction. So that's going to be right here. Increasing is on this side. So increasing is over here. So when it's going that way, the x's or the y values are getting bigger. When it's coming this direction, the y values are getting smaller. So when x is greater than 0, the graph goes up when viewed from left to right. So the function is increasing for all x's that are greater than 0. And then when x is less than 0, the graph is going down. So all the values on this side of the graph have x's less than 0, and the graph is decreasing as we go from left to right. So the function is decreasing for all x less than 0. Go ahead and pause the video and attempt the check. Okay, so this time they're giving us the area of domain to look at. So they're saying for x is greater than 1. So if we go find x equals 1, which is a vertical line right here. So x is greater than 1 is everything to the right of that line. So to the right of that line, what is f of x doing? Is it increasing or decreasing? Well, all the y values along here are getting smaller from left to right. So this is decreasing.